Okay, good afternoon, ladies and gentlemen, and welcome again to your SETI Institute Colloquium series. My name is Frank Marchis, and I'm going to be the host today for this colloquium. So I'm going to start by introducing our speaker today, Dr. Ruth Murray-Clay. She received a undergraduate degree from Harvard and a PhD from Berkeley University. After spending some time as an Institute for Theory and Computation Fellow and the Smithsonian Federal Scientist, both at the Harvard Smithsonian Center for Astrophysics, she moved back to California and she became a faculty at UC Santa Barbara. She joined the faculty Department of Astronomy and Astrophysics at Santa Cruz last year. So welcome back to California. In 2015, she won the Ellen Warner Prize from the American Astronomical Society for a theoretical study of star and planet formation, works as a substantial contribution to other areas of astrophysics, including circumstellar environments and the dynamics of galactic center. So I look at her list of publications. I'm impressed to see there is 100 papers and abstracts, but what is more impressive is that they are very related to a wide range of dynamical analysis. She's using her talent in this field for various studies, such as she's our token science theorist for our direct imaging survey called GPI. She also has been working on extracting useful information about the solar system formation from equipable surveys like OSOS. So today, Ruth is going to talk about the origins of structures in planetary systems. Please join me in welcoming Ruth.
Thanks, Frank, and thank you for having me here. I'm happy to be here. So today I'm going to be talking about the origins of structure in planetary systems. I work on planets and the systems that they live in. And because it motivates me, and I think many people in my field, I'll start with the Earth. I would like to know, is Earth rare? You know, there are many things that I could mean by this. I could mean, are there planets out there with little green men shooting each other with phasers? And I'd really like to know. But of course, we're not quite there yet. So I'm going to ask a slightly different question, and that is the solar system rare? Is the system that Earth resides in common among the systems that we now know to be fairly ubiquitous around other stars? And the reason that I think this is an important question is if we want to go out and find planets that in ways that are important to us are like the Earth, we might be more likely to find them in systems that have similar types of histories. And as we go on, I'll tell you a little bit more about what I mean by that. And so in particular, you know, which stars are likely to host planets similar to Earth? Which solar systems are like ours? All right, so one of the first results that came out in the study of extrasolar planets, this is now way back in 2005, was this result, showing that the frequency of stars that at that time were known to host planets was a strong function of this factor here, which is called stellar metallicity. This is iron divided by hydrogen, but astronomers call anything that's heavier than hydrogen or helium a metal. So we have to live with that terminology. What this means is stars that have heavy elements. So in other words, all of the elements that make up us and our planet here on Earth are considered metals. And if you're rich in those elements, you're more likely at this point to be known to host a planet. So if that's the case, should we search for Earth analogs around high metallicity stars that have a lot of iron in them, and by extension, other heavy elements? And because I'm asking this at the beginning, I think you can guess that I'm going to argue in the end the answer is no, not necessarily. All right, so let's take a look at our solar system. Here's my diagram of our system. The sizes of the orbits here are to scale. The sizes of the planets, of course, are not to scale. And because I'm a theorist, this system has 4 Earths in it. There are 4 rocky planets, and 2 Jupiters, 2 gas giants, and 2 Neptunes, 2 ice giants out in the outer regions. And then here we have our asteroid belt and a remnant planetesimal belt in the outside containing Pluto. That's what we now know to be the Kuiper belt. All right. So now let's remind ourselves of what's known about planets around other stars other than the sun. So when I was in high school, the answer was 0, and now we know a whole lot more, of course. So the first technique that was used to discover planets, oops, this isn't the first technique, this is the second technique. The second technique, the technique that's come up with most of our planet discoveries, thousands now, is known as the transit technique. As a planet passes between us and the star that it's orbiting, we see a dip in the light coming from the star. NASA's Kepler spacecraft has used this to great advantage to find a large population of several thousand high-quality planet candidates. If we put them on this plot of the solar system, they're all right there, right in the middle, right next to their star. And if we take a look at them, you can see what they look like. Here are a couple thousand planet candidates. On this axis is the period, so the distance from their star. Out here is where Earth would be. Here is the planet radius. This is the Earth's radius. This is Neptune's radius. And Kepler found a huge population of planets that are small out there around other stars, and showed that almost every star in the sky hosts a planetary system. Now down here, there are not planets sitting in the location of the Earth. That's just because Kepler didn't quite get that far. That's a selection effect. It couldn't see planets as small as the Earth and didn't have long enough to look, in part because its reaction wheels didn't last long enough. But Kepler showed, again, that small planets are common and that planetary systems are ubiquitous. All right, the second method, which is actually the first one that was used, is the radial velocity method for detecting planets, in which a spectrum is taken of the host star, and we look at the shifts in the lines coming from quantum mechanics in the spectrum as they go back and forth as the star moves under the gravity of the planet. You see this radial velocity curve. And this method can see about out to where Jupiter is in our planetary system. Okay, so it sees farther out, but it can only see bigger planets. And here's a summary of what's been found by the radial velocity method so far. Here's, again, distance from the star. This is mass of the planet. Here's Earth, Neptune, Jupiter. You can see most of the things found by this method are higher mass planets. Again, Earth can't be seen just because this method isn't sensitive enough. Okay, so we'll come back to this plot. But I want to point out, another well-known fact about the planet population, which is that most of these radial velocity detected planets are giants and they have very high eccentricities. So their orbits are not very circular. They're very elongated, very elliptical. And if you look at the solar system giants, Jupiter, Saturn, Uranus, and Neptune, those that would be analogous potentially to these observed planets, they have very circular orbits. Their eccentricities are almost 0. All right, so if we, and the last method that's really starting to come into its own, as Frank mentioned, is direct imaging. So actually taking pictures of planets around other stars. A few systems have been found at wide separations. I'm going to come back to this one. This is Neptune's orbital distance. This is the system HR 8799 with 4 directly observed planets. The takeaway from all of this is that the solar system's architecture is not typical. We found planets that are super-Earths. They're a little bit more massive than the Earth, but less massive than Neptune. Around many stars, maybe about a third of the stars in the sky from Kepler, and we have no planets like that at all in our solar system. We see high eccentricities from radial velocity planets. That, again, doesn't look like our solar system at all. So the systems that we found don't look like our solar system. And that might matter, right? Because if you have a Jupiter that's careening through on a really elliptical orbit at the location of the Earth, then that's not going to be a good environment to make an Earth-like planet, or at least a planet that has nice seasons that we're used to. Okay. So it's not typical, but it could still be common because, as we saw from those diagrams, again, the location of the Earth, the location of the solar system planets are right on the edges of detectability given current detection techniques. So the solar system's architecture is clearly not typical, but it could be common. And the question is, if we want to find systems that are like the solar system, where should we look? All right, so let's take a step back and think about how planetary systems form. So this is the canonical Orion star formation region. Here we see in these insets little disks around forming stars, and this is the site of planet formation. Here's another less extreme star formation region. This is an infrared dark cloud. This is about to collapse under its own self-gravity. And as it collapses, It, of course, will have a little bit of angular momentum. And what that means is that the collapsing gas will form a disk made of gas, dust, and as long as you're far enough away from the star, so you're cold enough, ice. And in this disk, the debris from star formation is where we make our planets. All right, so if we take a little chunk of that disk and ask, how quickly can planets grow, we can use a couple of rules of thumb to get a sense of, how quickly things can grow. The first is that the growth time scale increases as the orbital time scale increases. So as it takes longer to move around the star, it takes longer for these particles to collide with each other, longer for planets to grow. And as you move away from the star, your orbit takes longer. So it takes longer time in the outer disk. The other rule of thumb is if you have more material to work with, then your growth will be faster. Okay, so this can lead us to the standard model for how you form the structure in a planetary system before exoplanets were found. In this model, you had small rocky planets in the inner part of the system, like the Earth, where just there wasn't that much material, so you could make puny things like Earth. You go out farther, and two things happen. First, you end up with more material. You have more material both because you just have more area to work with, so you just have more overall material in your disk at larger distances. Also because as it gets colder, you can end up being cold enough to form ices, and so in addition to your rocks, you can have ices. If you have more material, then it's easier to generate a larger solid body. If you have a large solid body, you can accrete a really massive gas atmosphere. Once your gas atmosphere is as massive as you, then so now you're twice as massive. You can accrete another gas atmosphere that's as twice as you, and the whole thing can run away. You end up with a Jupiter, a gas giant. Go even farther out in the disk, and now it just takes a really long time. And if you just take so long that you can't form that big ice ball until the disk is almost gone, then you can end up with an ice giant. So Uranus and Neptune are only 17 Earth masses as opposed to Jupiter's 300 Earth masses. They're actually mostly balls of ice with only a relatively small, compared to Jupiter and Saturn, gas envelope. All right, so that worked perfectly well for the solar system, but of course now when we look at exoplanet systems, this doesn't work, at least in this form, for all of those systems. So what do we do? So we could either entirely throw this out, which I'm not going to advocate for. If I thought that, I wouldn't have shown it to you. Or we can see, what else is needed to make this picture work. All right. So my overall goal, and I'm not going to go through all of this, but I just wanted to tell you a little bit about where I'm coming from, is to understand, how the physical environment of a star that's growing forms a disk around that star, how that disk evolves, how you can make planets out of that disk, how they interact with the disk and migrate through it, evolve dynamically over long time scales, and ultimately, how the properties of those planets, including their atmospheres, evolve over that time. So I like to think about all of these processes together to try to understand what's most important for a particular question. So today, again, what I'd like to understand is under what circumstances does giant planet formation permit Earth-like histories for terrestrial planets? Okay. So let's start. I'm going to take a chunk of time now to talk about this system. This is a very unusual system. It's called HR 8799. I showed it to you before. This is a directly imaged system discovered in 2010, or 2009 actually, showing 4 very massive planets at very wide separations from a star that's a little more massive than the sun. Now, this system is very unusual, but what's really nice about it is that it's a good testbed for planet formation theories. And the reason for that is that all of the standard planet formation theories that existed before exoplanets worked don't produce the system. They completely fail. So either way, either we have to adjust that planet formation story that I told you to make this system work, or we have to say that actually, well, this isn't a planetary system at all. Maybe this is the tail end of star formation in some weird way that we didn't understand. Okay. So are these big planets or small stars? So why would I ask whether they're small stars? Well, these are actually 10 times the mass of Jupiter, approximately. So these are quite massive as planets go. All right, so there are three ways to form companions. So let's think about this. We can have turbulent fragmentation. This is the way we think that stars form. Typically, you have this cloud of gas and dust. We said it was going to collapse and form stars. There's turbulence in that cloud, so the material is being moved around in a random way. And if you end up having two clumps collapsing near enough by to each other, they can be gravitationally bound, and you can end up with two stars forming in orbit around each other. And this is how we think multiple stellar systems form. Most stars actually are in multiple systems. Unlike the sun, most have companions. Another possibility is called gravitational instability. In this case, you form a star, you have a disk, and you actually directly collapse the disk to form a planet under its own self-gravity after the disk has formed. And then a third possibility is core accretion. And this is the standard model that we think formed Jupiter and probably formed most of the planets that are giant planets in the galaxy. Okay. So in this model, you have this small solid material. It grows until you get a giant core, a solid body more massive than Earth. As I described before, it can then run away, accrete a massive gas envelope. Okay. So turbulent fragmentation produces multiple stellar systems all the time, but when you look at multiple stars, they don't usually look like that image that we had of the HR 8799 system. They don't usually look like one star in the middle with four orbiting around it. Instead, they look more like this. You'll have two stars orbiting each other and the third one very far away. So this is called heirarchical. This is a typical architecture that you get. Since HR 8799 is not hierarchical, it's unlikely that it formed by turbulent fragmentation. So that leaves us either gravitational instability, core accretion, or you could have a situation where you formed your planet closer to the star, where it was easier to do, and then it was scattered outward. Now, this is very plausible. We think this happens all the time, but you can't really make four planets nearby in the same system this way. If there was just one, it would be good. But I'm going to cross this off because we have four in this system. You could also make more complicated hybrid scenarios. That's really fun to think about, but I'm going to stick with these for now. Okay, so gravitational instability. This happens when self-gravity in your disk overcomes both pressure, which, you compress a gas, it wants to expand again, and tidal gravity. That means that as material is, moving through the disk, it wants to shear apart in order to collapse under its own self-gravity. And this happens, the most unstable scale for this is the scale height of the disk. So it's easiest for it to collapse on a length scale equal to the thickness of the disk. So you can write down the mass of a fragment that you'd expect to get by this mechanism, just to order of magnitude, and you get something that's like the thickness of the disk times the mass of the star. And we went ahead and did this back when the system was discovered, and found that you could actually make the system by gravitational instability, but you have to tell a really specific story. So I'll tell you what the story is. So here's distance from the star. Here's the mass of the planets. Here's 10 Jupiter masses. That's what I said you were. These are these four planets that were discovered. And here's what we found. The minimum fragment mass that you would get given reasonable disk temperatures. And it cuts off here at a minimum fragment distance. That's because as you get too close to the star, you can't actually cool quickly enough to allow fragmentation to happen. So you can put this on here, and you can say, okay, these planets are about the mass of the minimum mass, but they can't grow after they fragmented, and they have to move in closer to the star. Now, you might think that the moving in was actually the hardest part, but it turns out that it's not. Again, when this system was discovered, my collaborator, Dan Fabrici, put it into an n-body integrator and found that given, at the time, the nominal orbital parameters of the planet, they fell apart, dynamically fell apart in a few thousand years. So that's bad. The system can't fall apart in a few thousand years. It's been around for millions and potentially millions of years. So it's a pretty young system. So what we found, actually, is that in order to make the system stable, you have to put these planets in what's known as mean motion resonances. And mean motion resonances are a particular dynamical state that can be generated by migration. So if you move through your disk, you can capture into resonance. So that actually means that maybe these things did move in, and that's why they're in that particularly dynamically stable state. Okay, so here it is. I'm just going to show you the cartoon. Here's what you have to do to make the system by gravitational stability. So you start with a cloud. It's accreting onto the disk. It's accreting really quickly. A disk can't just go unstable by out of nowhere. It has to have gotten that way somehow. You have to have added material to the disk until it got massive enough to go unstable. You can't just poof it from the void. Okay, so you're accreting onto the disk to try to make it more massive so you can collapse. As you do that, you make it massive enough that a planet forms. Okay. And then if the disk keeps growing, you have a problem, because the material that's coming in onto this disk, trying to make it onto the star, won't just jump over the planet. It'll actually get accreted onto the planet and make the planet grow bigger. Okay, so it'll grow and then it'll become a star. So you don't end up with a planetary system, you end up with a star with another, maybe smaller star orbiting around it. So that second part was actually the biggest problem. They can't grow after they've fragmented. So what can we do? Well, here, okay. You start with a cloud, it collapses, it grows, you make 4 planets in it, and then they open a gap in the disk. You immediately stop accretion, just at the right time. They migrate in. Okay, I'm just going to use my arrow keys here. The disk goes away, and ta-da, you have the system. Okay, so it works. Actually, there's no piece of this that doesn't work, but it has to happen in exactly the right way. You have to cut off that accretion just at the right time. And so, here, when my collaborators Caitlin Cratter and Andrew Uden and I started thinking about this, our concern was that, if you are going to cut off that accretion just at the right time in this system, then most of the time that this happens, you shouldn't be so lucky, and you should end up with a multiple stellar system. You should end up with a star orbited by a low mass star. Okay, so can we look at the data and see if that's reasonable? And this plot, it's old now. It's also a plot with the most selection effects you have ever found. This is not a uniform sample in any way, so don't think of it as one. So let's look at separation from the star, and this is mass of the companion divided by the mass of the star. And in the bottom left here, we have our planetary companions. Most of these are from the radial velocity method. In the top right, we have our brown dwarf companions. These are low mass stars orbiting their host star. Out at the right-hand side of the plot, this is larger than the size of most protoplanetary disks. So we're pretty confident that those formed through turbulent fragmentation through that star formation process. And then right there, right in the middle, is HR 8799. Right. So it could, just looking at this plot, it could be part of those that brown dwarf population, or it could be part of the planetary population. Okay. So if we want these to be formed by gravitational instability, they have to be failed binary stars. There should be some binary stars sitting in that part of the plot. Okay. And so I'm going to get to in a moment. Well, I'll tell you that it doesn't look like this is the case. So I'll show you an image a little bit later of one of the giant planets that's been found by, as Frank mentioned, the Gemini Planet Imager exoplanet survey. A lot of effort has gone into trying to find companions at these distances around these sorts of stars. And a few have been found, but not very many. So it really looks like this system is probably not part of a big population of binary stars. We probably have to make that standard core accretion model for planet formation work. So what's the problem with it? The the long-standing problem with making core accretion work at wide separations is known as the last doubling time. So as I said, as you go farther and farther from the star, it takes longer for solids to collide with each other. And if it takes longer, then eventually it's going to take too long. You're not going to be able to make a planet on the timescale needed to accrete a massive gas envelope from a disk, because disks only last a couple million years. All right. So, but there is a way that we can potentially save ourselves. And that's to recognize that if you have a larger cross-section for accretion, so your accretion rate is given by your area, your cross-section for accretion, times your velocity, times the number density of things that you're colliding with. If you can increase that cross-section, then you can make accretion happen faster. So there's standard cross-section regimes for accretion. The first one is just the physical cross-section. You have a core that's trying to grow, is trying to collide with small bodies. If they hit it, maybe they can be accreted. The next regime is called the gravitational focusing regime. If these small bodies are going at a small velocity, they can be focused by the gravity of your core and accreted from a larger distance. They could be captured by gas drag into a planetary atmosphere if it's there. But even with all of these regimes, at the distances of the HR 8799 outer planets, it's too slow. All right. But what's been recognized in the last few years is that we can actually make gas useful to allow accretion over a much larger cross-section. This is how it works. So here is our core in the middle. This is actually a numerical simulation that I ran. Here's a planetesimal, a small body, coming in, and it's being captured into orbit around the core. And then the orbit is decaying until it collides with the core. And this cross-section that this can happen over is not the physical size of the planet. It's not even the gravitational focusing radius. This is what's known as the Hill radius. It's the distance out to which you can actually have a stable orbit around the core, which particularly in the outer disk is much, much larger. So here, and then the key thing here to know is that this depends a huge amount on the sizes of these planetesimals being captured. That's why this took a while to be recognized. Small bodies, millimeters or centimeters in size, work the best. These pebbles come in, and they can actually be captured by gas drag from the disk and accreted more effectively. All right. So if you have no gas, satellites can orbit within what I call the Hill radius. You can go around the core. You have to modify this if you have gas. Then it can actually pull objects out of orbit, even if they could have been able to orbit. So this actually ends up being quite a complicated problem. If you have a large body, then its surface area to mass is small. It's not affected by gas drag that much. If you have a small body, its surface area is large compared to its mass. It can be pulled by the gas most effectively. If it's pulled too effectively, it'll just be whooshed off of the core. And so we call this the wish or whoosh radius. So now you have a distance within which you can be captured. And within that capture, if gas drag can dissipate your relative energy as the particle approaches, then it can be captured in a binary capture process and accreted from large cross-section. Okay, so here's another, just to show you that it works in a simulation. Here's that gravitational Hill radius, the tidal radius, or otherwise known as the Roche lobe radius, and you can see particles being captured onto this core from all the way out to the Hill radius. And if you use this process, growth timescales, even out at the 70 AU distance of the outermost HR 8799 planet, can be short enough to nucleate an atmosphere. And this is an example using just 50% of the minimum mass solar nebula in solids in small bodies, showing that it can grow very quickly to critical. Okay, now turbulence in the gas doesn't prevent the final stage of growth. This is a simulation, I'll play it one more time, showing that this process works even in turbulent gas. This is done by an undergraduate named Zian Zhu and Shearing Bai, who's a postdoc now. We showed that you get capture even in a turbulent gas disk. And you can see this happening here. That doesn't mean that turbulence is not important. And actually, one of the problems with gas-assisted growth or pebble accretion is that it's embarrassingly effective. Right? If I can make a giant planet at 70 AU in the HR8799 system, why the heck don't we have one? Right? So in an attempt to answer that question, I have a great graduate student right now, Mickey Rosenthal, who's been working on this, working on how this growth process works in a turbulent gas. So this alpha parameter here is a dimensionless number that just parameterizes the amount of turbulence that you have in a disk. Here's a non-turbulent disk, one with low turbulence, moderate turbulence, and high turbulence. And you can see that the amount, this is the growth time scale for particles of a particular size. And you can see that as you go to higher and higher turbulence, there are fewer and fewer particle sizes that allow you to have a small growth time scale. So these are just this is down at, this is centimeters, millimeters, meters here. Exactly what these numbers are depends on your disk properties. But you can see there's a range of a few orders of magnitude of relatively small planetesimal sizes. And whether this works depends on the level of turbulence in your disk. Okay. So just to show that you can, here's as a function of core mass and particle radius, pebble radius. This tells you the growth time scale. You can see that you can accrete a wide range of pebble sizes in a non-turbulent disk, but in a very, very turbulent disk, you're eating out of that range. So as you make things more turbulent, it becomes harder to accrete. Okay, so where am I going with this? Where I'm going with this is that now as your distance in your disk, the growth time scale goes up with distance in your disk. Your growth time scale at high turbulence is higher than your growth time scale at low turbulence. This is for a particular core mass. So what we can do is we can say that if you go out in your disk, the maximum, if you want to be able to make a giant planet, you need the maximum mass that you can achieve using standard growth processes to be at least as large as the minimum mass that you need to use pebble accretion to grow to make a critical planet. So if we put these two criteria together, then for this level of turbulence here, which was an alpha of 10 to the minus 2, you can see that that criterion is only satisfied interior to 40 AU in a disk. All right. So our hypothesis is that turbulence actually sets the scale where you can form giant planets in a disk, but it's not through this allowing the standard last doubling of your core, which is what was previously the problem. The last doubling is always fine. Turbulence causes problems earlier on in the growth. All right, so that's our working hypothesis for the moment, and we can turn that into a distance that you can form cores out to as a function of the level of turbulence in your disk. And you can see that that distance ranges all the way from 20 AU all the way out to 80 or 90 AU, depending on your particular disk's turbulence properties. Okay, so that might be the answer. All right, so let's go back to this. Plot here. Our point was to say, well, if the HR8799 planets were connected to that brown dwarf population, then maybe they formed by gravitational instability, and that could also form brown dwarfs, low mass stars. Or maybe they're connected to the giant planet population, in which case perhaps this gas-assisted growth or pebble accretion scenario that I talked about could explain why you can get planets out that far, and maybe turbulence explains why you don't always get planets at those distances. All right. So as I mentioned before, the Gemini Planet Imager Exoplanet Survey has been looking in this region. And while it has made some exciting discoveries like 51 Eridani b, it hasn't actually found as many objects as were expected. So this is pointing toward a planet formation type process for HR8799. All right, and I'll leave that summary here. Okay, So I'm just going to very briefly point out that there are other ways of trying to distinguish formation processes. For example, you can look at the atmospheric composition of your giant planets. This is just a very simple version of an idea that that's been a lot of work has been done on now to try to flesh out more. If you are looking for planets that form by core accretion within the water and between the water and CO snow lines, so carbon monoxide and water snow lines between 2 AU and 40 AU, in other words, where we think most giant planets are formed, then they're being made out of solids that are oxygen rich and gas that's carbon rich. So if you make your core out of mostly those oxygen rich solids and your envelope out of carbon rich solids, you can have a carbon rich atmosphere. Alternatively, if you take this and then you throw a lot of oxygen rich solids at it, you'll end up with an oxygen-rich atmosphere. So we can, whereas for gravitational instability, you wouldn't necessarily expect to have that same compositional signature. So there are other ways that we can try to distinguish these mechanisms. All right, so now for the rest of my talk, I want to take this discussion from the distant giant planets and move it closer to our stars. And then we'll get to the question that I asked at the beginning of the talk. Okay, so here's this radial velocity population of planets that I started with. Here's semi-major axis as a function of planetary mass. And if we look up here, these are the giant planets. The giant planets, incidentally, we care about the giant planets when we're talking about the structure of planetary systems because those are the ones that set the dynamical stability of your system. The more massive your planet is, the more likely it is to have dynamical interactions with its neighbors and cause them trouble. So if you look at this plot out here, there's a big uptick in the frequency of giant planets that are seen. Now, this isn't a uniform sample, but these would be easier to find, and these are harder to find. So since we see an enhancement in the population out where they're harder to find, it's likely real. And we can look at this plot in a slightly different way. This is a plot from a graduate student of mine, a former graduate student. She's now a faculty member at Penn State, Rebecca Dawson, looking at the distance from a star versus the 1 minus the eccentricity of a planet's orbit. So this is 1 minus eccentricity. This means these are really elliptical orbits down here. These are circular orbits up here. And I want to point out a few features of this plot. So we've colored this in different colors. I'll tell you what the colors are in a second. Over here, where we see this big uptick in the giant planet population, this is where we think giant planets likely form most of the time. If we look in very close to their stars, we see the first population of planets that were found. They're only about 1% of stars in the sky, and they're known as hot Jupiters. They're circularized because tidal interactions with the star circularize them. And there are a couple of theories for how you can get a planet that go from out here, where we think most of them form, in close to their star. I should also say that people have suggested recently that maybe planets can actually form closer to their stars than we think. But if we want to move them from out here in, you can either do that through disk migration, where they basically stay circular the whole time. They're raising perturbations in the gas disk that they're forming out of. Those torque the planet and move it in. Or you can have them move in by what's known as high-eccentricity migration. So you have your planet, and it's starting at a very high eccentricity. What that means is that even though its semi-major axis, so its scale of its orbit is large compared to the star, it's so eccentric, it's so elliptical that it actually passes close by the star. Tidal interactions cause its its orbit to be damped, and it can move along a path like this until it becomes a hot Jupiter. So Aristotle Socrates suggested in 2012 that if this process was actually happening, there should be enough information in the Kepler survey to see it. And Becky Johnson and John Johnson actually developed a method that we could use to do that. It's called the photoeccentric effect. As a star that's on an eccentric orbit passes by with the same semi-major axis with the same period, it goes by faster than a star on a circular orbit. So you can make a statistical measurement of what the eccentricity distribution of these planets might be, particularly for very high eccentricity ones. And we actually looked at the Kepler data with this in mind, and were able to rule out this pathway for most of the hot Jupiters. So what that means is that evolution inward due to interactions called Kozai oscillations with stellar companions cannot actually generate, those can produce these really high eccentricities, but they can't produce this hot Jupiter population. There could be dynamical interactions that could kick up hot Jupiters to higher eccentricity orbits sort of in this intermediate region, which we call the period valley. And in fact, if we look at those, we do see some planets that could be along paths like that. Now here I'm going to tell you what our colors are. Red means low metallicity stars. Remember I started talking about metallicity. And blue means high metallicity stars. And you can see that the planets that are along this path are around high metallicity stars. Why might that matter? Well, if you have high metallicity, you might be more likely to have another giant planet in your system that kicked you up to that high eccentricity that allowed you to be on this path. Okay, so that was, this is for a different sample of planets. But now we have our key on here. You can see again, red is low metallicity, blue is high metallicity stars. You can see these high eccentricity planets sitting in the middle here are blue. Those tidally circularized hot Jupiters are also blue. And in fact, if you look at the Kepler sample of planets and separate out the full sample, this is period. These are the ones that are very close to their star, the hot Jupiters. This is number of planets. There's what was one of the earliest results from exoplanets was that there's a pileup, an increased number of hot Jupiters around very close to their stars. And you can see that here around the high metallicity stars, but not around the low metallicity stars. So this was radial velocity planets. You can see that there are different features around high and low metallicity stars. This is Kepler planets. That's an entirely different planet sample. You can see those different features. And our interpretation of this is that metal-rich stars host more hot Jupiters and highly eccentric planets because these are signatures of planet-planet interactions. So if you make a lot of giant planets in your system, you're more likely to have dynamical upheaval that puts you into a position to be either very highly eccentric or to have been brought down this pathway to be a hot Jupiter. So if high metallicity stars mean you make a lot of giants, which means you have a lot of dynamical interactions, then we're starting to get back to that question that I asked at the beginning. If we want to look for systems that host planets like the Earth, if we want to look at solar systems, should we be looking at the highest metallicity stars? And I think that if this is the right interpretation, the answer to that is no. If you look at the highest metallicity stars, you're going to be making too many giants. They're going to be dynamically interacting, and they're going to be, this is 1AU, this is where Earth is. They're going to be causing a mess right around the Earth, which is where we would like a nice dynamically clean region to exist to make an Earth-like planet, at least Earth-like in its surface properties, not just in its size. Okay. So just to show this again in another way, I'm going to show these radial velocity planets. The blue, again, is the high metallicity stars. The red is the low metallicity stars. Here's distance and mass. You can see the blue, the high metallicity stars, these planets have been smeared out throughout this whole region, dynamically smeared. If you look at the low metallicity stars, there are still giants out here, but they haven't been smeared out into this region. If you go in closer to the star, you're more likely to see lower mass planets. So I can put these on top of each other. is to see it again. So if we're looking for a nice stable Earth, you might prefer to look among these. Okay, so my hypothesis then is that solar system analogs are orbiting moderate to low metallicity stars. Another way of saying this is that the planetary systems that it's easiest for us to find are not like ours. So if we want to find the planetary systems that are like ours, we don't necessarily want to look at the stars that are most likely to have the planetary systems that are easiest to find, right? Because those are not the ones that were like ours. Okay, so let me take sort of a bird's eye view of all of this and sort of defocus the complicated physics of planet formation and see if we can make sort of a really, actually very simple, but I think powerful description of what might be going on here. Okay, so here are my assertions. First is the solar system exists. I'm comfortable with that. Okay, I'm also going to assume that it isn't a bizarre statistical fluke. It always could be, but I'm just going to assume it's not. I'm also going to assume that only a few controlling parameters determine the diversity of outcomes when it comes to the structure of a planetary system. Okay, so that, for example, could be the stellar mass. It could mean the solid mass and the disk that's making the planets, and you can use metallicity as a proxy for that. It could mean the accretion properties of the disk. It could be the stellar environment, like are there other stars nearby when you're forming your planetary system. I could add a bunch more to this list, you probably could too. But there still aren't going to be as many as knobs you can turn in planet formation theory, because we have a lot of knobs that we can turn. Okay, so can we pick one, and then you can pick another one and pick another one, and but I'm just going to pick one today, and see if we can understand, what the different structures of planetary systems are based on that parameter. Like, how important is it? Can we actually see a signal in the different structures based on that parameter? And I'm going to pick solid mass in the disk, or with its proxy, metallicity. Okay, so I'm going to show you a cartoon. And planets that have a rocky solid component are going to be brown. If they're an icy solid component, like Uranus and Neptune, it's going to be blue. Red will be a gas giant. I'll put lines if I'm going to suggest that they're mixed. Composition within a planet, and then the little circles if that means mixed orbits. So like they've dynamically interacted and mixed up where they are. And again, you can do this in several different ways, but here's one example of such a plot that I made with Leslie Rogers, and we're writing this up. So here on the y-axis is the disk mass. This is the distance from the star. I don't have any numbers on this on purpose, because this is intended to be a diagram. I don't have a scale on this either, because I don't know, relatively how big each of these phases should be. But you'll see in a sec what I want to do with this. Okay, so here is the solar system. It's on here because it exists. That was one of our defining assumptions. And here we have rocky planets in the inner part, gas giants in the middle part, and ice giants in the outer part, for just the reasons that we said at the beginning of the talk, for the pre-exoplanet structure calculations, right? Okay. So now let's say that you actually put more solid material into your disk. Now it's easier to make bigger rocky planets, but it's also easier to make gas giants. So the region where you can make your gas giants expands. You can still make ice giants in the outer part. You go up and up and up. You might even be able to make gas giants all the way in close to your star. But eventually, you make so many gas giants that you have a dynamical jumble. And I was arguing that actually maybe a large fraction of the radial velocity systems that we're seeing lie up here in this jumble, the dynamical jumble. Okay, now if you go from the solar system and you go down in solid mass, eventually you can't make gas giants anymore. Maybe you can start making mini Neptunes, icy rocky objects that could migrate all the way in to where Kepler could see them, perhaps. Kicking other material out as they did so. If you go even lower mass, you end up just with a little bit of solid debris at the bottom. Okay. So this could, if disk mass is telling us what structure you have in your planetary system, it could be organized in this way. And what would the consequences of that be? Well, first, let me just point out that this really simple diagram can't yet be ruled out. This isn't proving anything, but this can't be ruled out. Here are some systems. We just picked some systems and tried putting them on. Here's WASP-47. This is a super funky system that has an Earth, a Jupiter, and a Neptune in a weird order sitting right next to their star. It's a really high metallicity system. Dynamical jumble. If you take a couple of these Kepler systems that have both inner either super Earths or mini Neptunes, rocky objects, and some gas giants, they're relatively high metallicity systems. The solar system in this scale is metallicity 0. Incidentally, when I did that cut for the blue and the red, I did it at solar metallicity. It doesn't really matter exactly what you pick, which is good because you don't want it to matter too much, but it was at solar metallicity. And then you go down to some of the other Kepler systems where we don't see giants, and they have lower metallicity. This doesn't prove anything because we don't actually know exactly what is out in the outer regions of all of these systems, particularly the Kepler systems. But you can't rule it out. It works so far. Okay, so here's one example of something that you could do to test this framework for understanding how systems behave. Well, you could say, well, let's take those Kepler planets, those ones that are more massive than the Earth, or larger than the Earth, really, not as large as Uranus and Neptune. Let's say they're rocky, they're super Earths. This diagram says they should have giants at larger distances. But on the other hand, if they're ice balls that migrated in from far away because they just, they never got, by the time they got big enough, the gas disk was gone, they didn't have enough material to become a gas giant, then if we look in those systems at larger distances, there should be no giants. So what we could do is say, let's take some systems that don't have any of these super Earths or mini Neptunes, and some that do, and look to see if they have different radial velocity trends at large distances. Even if we can't wait 20 years to see if the planets are there, we could do a binary comparison to see if those systems are different. And observers are starting to look for this. So I'm excited about that. And we could do that. If we do that, we can test some of our really sort of, I would call these vanilla assumptions about how planet formation works. All right. So I'm going to end there. I started with the question, under what circumstances does giant planet formation permit Earth-like histories for terrestrial planets? I talked about giant planet formation processes, and I gave you the hypothesis that the solar system's calm architecture reflects formation around a moderate to low metallicity star. So one where it's actually harder to find planets because our planets are harder to find. And I showed you these two observational tests of some of these ideas. Our HR 8799 planets, are they brown dwarfs, or as is looking more likely, are they part of the giant planet population? And if we get very different architectures around different stars from core accretion planet formation, can we understand the differences in those architectures through controlling parameters like disk mass? So, thank you.
Thank you. The floor is open for questions. I'm going to start with our local theorist at the SETI Institute.
Thanks, Ruth. It's a great talk. I have one question about the same major axis eccentricity diagram. You still had quite a few low metallicity planets beyond 1 AU on eccentric orbits.
So if you have just a few planets, so it's actually dynamically difficult to bring planets in closer to the star, as you know. So our, at least the qualitative hypothesis here is that if you have a couple of planets interacting, they can kick each other up. But if you really want to move them into low angular momentum orbits, you probably need more giant planets.
I was going to ask, is there any selection bias there? Because maybe for the same major axis, you would have easier time detecting eccentric ones?
Not that I'm aware of for the radial velocity method. If you have any thoughts, I'd be happy to discuss them. In fact, they can actually be harder to find because their signals look a little more odd.
In your thoughts about the formation of planetary systems, you point out there were a lot of parameters that one might pick that might influence the outcome. One of the ones that you listed were stellar mass. Does your model tell us anything about what we'd expect from M dwarfs versus G dwarfs? I think it's particularly pertinent as tests will fly soon.
So I think that it's hard to say a priori what I'd expect. Other than that, we think that based on the lower frequency of giants in general that have been found around M dwarfs, and the expectation that their disks will be less massive, that's at least consistent with this, qualitative picture, which I'm not necessarily taking credit for the idea that, well, I'm definitely not taking credit for the idea that if you have a lower mass disk, you'll have fewer planets. I mean, that's, again, just a very vanilla planet formation idea. In terms of how wide separation you might be able to get your planets, if we're correct that the turbulence structure of your disk is really important there, then I think we will see something, interesting in the relationship between M dwarfs and G stars, because the ionization from the host star can affect the turbulence, structure of your disks strongly, and M dwarfs have comparatively more, ionizing photons. But we have so little in terms of, exact observations about. Well, we don't understand how accretion behaves on a very basic level. So I don't think I'm going to be able to give you a clear prediction.
Hi. Thank you for that talk. I expect it'll be nice background info for tomorrow's NASA announcement. But in any case, my question is about, you mentioned all the various parameters, but you didn't really talk about multi-star systems other than the fact that they were more common. And I'd heard a previous talk about the Alpha Centauri system, and that there were limits in terms of AU that planets could form stable orbits around the binary system, not taking Proxima Centauri into consideration. So I was wondering what the metallicity of Alpha Centauri A and B are, if you know, and what how it would affect a solar system on that chart on the bottom right if there's a companion star that's ripping out the things on the far end of distance from star.
So multiple stellar systems can affect things in various ways. I don't actually, off the top of my head, know the metallicity of Alpha Centauri. Does anyone know? No, I don't. Okay. So in the inner regions of the disk, as you alluded to, you can have unstable orbits if you have a binary star in the middle. So it'll just cut out the middle. And in the outer regions, you can also have unstable orbits if you have a wide separation binary. The observational information that we have so far suggests that the frequency of planets when you're in the stable region of multi-planet systems, that's not particularly interior to a wide separation binary, is not so different from if you're around a single star. So if you have a wide separation stellar companion, the inner region may be fundamentally unchanged. If you have an interior binary, then it may provide additional excitation to the orbits of small bodies nearby and could have a more profound effect on what's happening in the planetary system. But once again, once you're far enough from that stability boundary, it may not be that different. But I'd say we don't have enough information to know whether the circumbinary planet population is going to be fundamentally different.
I have a question while I'm working there. This diagram is interesting because you describe different type of planetary systems based on planets only. But the planetary systems are not only planets; they're also small solar system bodies.
Absolutely.
So, what can you extrapolate this diagram and say what you expect if you were able to see small solar system bodies, the signature of small solar system body? What will happen in all these different categories of the diagram? I mean, the top one is easy, but then I'm kind of curious to see what's going to happen when you have a very low disk mass. Do you expect to still see asteroids and or comets or any structures in this case?
I'm just thinking off the top of my head here.
I love that.
But I might even expect to have more structures in this case because more of your system is going to remain stable. So, what sculpts, where small bodies can exist in the solar system is stability, right? The other planets prevent them from remaining on stable orbits for long time periods, except in the asteroid belt and in the outer region. If you only have small planets, then they don't have as large a dynamical reach. So you might end up being able to keep a larger population of small bodies for longer.
Okay, so if we observe one of these Kepler system with a lot of very close planets, and we were able to detect transit or spectroscopic signatures of comets and so on, we will see more of them.
I have to think about it a little more than for 2 seconds, but yes, I think it's an interesting idea.
Let's think about that.
Yeah.
Hi, Ruth.
Hi, Peter.
So you mentioned both metallicity and disk mass,
Yeah.
but they're pretty much independent of each other, right? Because you can have an A star with a massive disk, but a subsolar metallicity, versus say an M dwarf with a puny disk, but a supersolar metallicity. So how would these things scale with each other?
Right. So I'm in making this plot, I've completely conflated them, but you're exactly right that they're not necessarily the same thing. I'm assuming here that it's solid mass that matters the most. And if you're looking at similar type stars, maybe you have some hope that you have similar total disk masses, and so then metallicity might be a reasonable proxy. Even that isn't guaranteed. But yes, I mean, it's the total disk mass that I think should matter the most here. And when I put those metallicity examples on here and showed that it can't be ruled out, I think that in a way it's almost surprising that you can't just rule this out immediately for that and many other reasons.
Okay, there is no more questions. Thank you very much, Ruth, for your talk. And as a token of our appreciation for coming here, you have this wonderful cup. Thank you.
Thank you very much.
Drink a lot of tea or coffee or whatever you
All
want.
right.
Thanks.
Great, thank you.
Thank you.